Hello everyone, welcome back to the MOOCs course on Advanced Analytical Technique. This is week 2 and the third lecture. This is the third lecture of the second week of this MOOCs course. In the previous few lectures, we have discussed about the atomic absorption spectroscopy and its principal working instrumentation as well as the possibility of interferences and how to avoid those interferences. Today we'll start with another technique which is very versatile and widely used in industries as well as research centers. This is called as atomic emission spectroscopy. In contrast to the atomic absorption spectroscopy, this technique is based on the emission spectrum. This atomic emission spectroscopy is a multi-element analysis technique which can be used even for certain elements for which atomic absorption fails to provide reliable data. For example, in case of atomic absorption, we cover the alkali metals, alkaline earth metals, and transition metals. And the scope of AAS is limited to 50 to 55 elements of the periodic table only. While the atomic emission spectroscopy, also known as AES or optical emission spectroscopy, OES, this technique can be used for the analysis of around 75 elements of the periodic table. In addition to the metals as well as metalloids, certain metalloids, this technique can be extended to lanthanides as well as few actinides analysis as well. Just like atomic absorption spectroscopy, the data provided by atomic emission is very reliable and robust data. But the major difference between the atomic absorption and atomic emission spectroscopy, this atomic emission spectroscopy does not require a light source. As I have explained you in the previous lectures, in the very first lectures where I was explaining you the difference between an absorption spectrum and an emission spectrum, there I told you that for absorption spectrum, a light radiation from a light source is needed that passes through the sample where interaction will occur and electrons and atoms absorb energy so that their electrons are promoted to the next higher level. This absorption creates an absorption spectrum. While in case of emission spectrum, I told you that in case of emission spectrum, we do not need a light source. We heat the sample, provide thermal energy either by heating in a flame directly or by giving an electric discharge, and then those atoms absorb energy and their electrons are promoted to the next higher level. When those electrons relax and comes back to the ground state, they emit light radiations and an emission spectrum is generated. So in atomic emission spectroscopy, we do not need a light source, which reduces the cost of the light source and which makes the equipment even more versatile and robust. But since we do not need a light source in this case, so we excite the sample by thermal energy, and therefore the thermal energy required in atomic emission spectroscopy is quite high as compared to the requirement of thermal energy or the requirement of heat in atomic absorption spectroscopy. So high thermal energy is needed, high and heat is required in this technique, because here the role of the atomizer is not only to convert molecules into individual atoms but to excite those atoms as well. So here the atomizer serves the purpose of atomization. Here the atomizer serves the purpose of atomization and excitation. In atomic absorption, atomizer only atomizes the sample, convert the molecules or the compounds into individual atom, while the excitation is being done by the light radiations coming from the holocathode tube. And since in this case we do not require a light source, so the same job of excitation which is being done by holocathode tube in the atomic absorption, here it is done by the atomizer itself. So we need extra heat for excitation of these samples to put those vaporized sample in excited state, not in the ground state. As I just mentioned, that this technique can be used to analyze around 75 elements. So you can see in the periodic table, we can these all these blue color elements can be analyzed. We have alkali metals, alkaline earth metals, we have transition metals, certain metalloids, and then we have all lanthanides and two actinides that can be analyzed with this technique. Someone may ask a question, sir, why atomic absorption cannot be used for the analysis of lanthanides or these elements as well as two actinides, while this atomic emission can be used? The answer to this question is that since atomic absorption uses low thermal energy only, it has only flame atomizers or graphite furnace atomizers that can provide temperature of up to 3000 degrees Celsius only. So the metals that can easily vaporized and dissociated in this particular temperature range can be analyzed by atomic absorption spectroscopy, while metals like these few requires excessively high temperature, which is not possible with normal flame or a graphite furnace. Such metals can only be analyzed by providing very high temperature, which is only possible by using certain other modes of heating like electric arc or an electric spark or maybe a plasma. Plasma is a very good source of energy for atomization as well excitation of the sample. In the later slides, I'll explain you more about plasma, what it is and how a plasma is formed and how much temperature it can achieve. So, as I said, atomic emission spectroscopy is another interesting and very useful analytical technique that is used for the qualitative as well as quantitative analysis of metals, ranging from alkali and alkaline earth metals to transition metals, certain metalloids, lanthanides as well as actinides. This technique is also known as optical emission spectroscopy. It works by measuring the intensity of the light emitted by the excited atoms when they return back from the excited energy level to the ground state. When they come back to the ground state, they emit light of a specific wavelength, which is a characteristic of a particular type of element, and from that characteristic wavelength we can identify the type of elements present in the sample, and in this way we can do the analysis, or we can analyze the sample and identify that what kind of elements are present. Here in this technique, both excitation as well as de-excitation occurs during the analysis. Excitation occur not by light but by the absorption of heat radiation provided by the atomizer, whose job is to atomize the sample as well as excite the sample. So resulting into excitation, and then which causes electrons to move to the higher energy levels from the ground state, and when these electrons return back, the process called as de-excitation, relax and come back, or we can also say relaxation. When they relax and come back to the ground state, they emit light of a specific wavelengths. Based on the light emitted by these relaxation phenomena, we can identify the structure of the compound, the composition of the sample, as well as its surrounding environment or its surrounding elements, what other elements or groups are present in the sample. Again, and this technique is used for both qualitative as well as quantitative analysis. Just like atomic absorption, atomic emission can also be used for qualitative as well as quantitative analysis. Once again, I would like to apprise you that qualitative means to know the nature of the compound, its structure and its type and behavior, while quantitative analysis means to determine its amount or concentration in the given matrix. the basics principle of atomic emission spectroscopy. The principle of emission spectroscopy, the intensity of the light or the amount of light emitted by the sample is directly proportional to the concentration of excited atoms in vaporized form of that element. If the intensity of the emitted light is high, then that means that those particular atoms are higher in number. The concentration of those atoms is higher in excited state, in excited vaporized state, and this is only possible when their concentration in ground state is higher. So high intensity of the emitted light means high concentration of the sample. On the other hand, if we have light with low intensity, it means the concentration of that particular element is low in the sample matrix. So the principle of atomic emission spectroscopy based upon this phenomena that the intensity of the light is directly proportional to the concentration of vaporized atoms in excited state, and it is directly proportional, and from the intensity it automatically measures the concentration or the quantity of those target analyte elements. Since the atoms or molecules, when absorb energy, they promote their electrons to higher energy levels, and we all know that these higher energy levels are not very stable, they are unstable states. So electrons immediately return back to lower energy level by releasing photons, by releasing or emitting light. So this is the phenomena of excitation. This is represented in this schematic diagram, where the electrons are getting energy, where the atom are getting energy and electrons are promoted to a higher level. And when these electrons return, because it is an unstable state, electrons decay back to your ground state, and when this process of deactivation or de-excitation or even relaxation occur, there is, of course, there is a release of light, which is the basis of emission spectrum. This light which is being emitted by the deactivation process, by the de-excitation process, then detected by a photosensitive detector, which measures the intensity of the light, which counts the total number of photons, and based on the total number of photons, it automatically calculates the amount of atoms or molecules that are present in the excited state and that are coming back from excited state to the lower energy state, because when they come from higher energy state to lower energy state, then they emit light. If the light intensity is more, then that means that atoms that are coming from excited state to the ground state is more, and that ultimately determines their concentration. So by measuring the amount of light, we can determine the concentration, and by measuring the wavelength of light, we can identify its structure. As I said before, in case of AS as well, since the spectrum consists of intensity on the y-axis while wavelength or lambda on the x-axis, this x-axis data is used for qualitative analysis, while the y-axis data means the peak height or peak area is used for quantitative analysis. Quantitative analysis. And for quantitative analysis, we need a calibration curve, while for qualitative analysis, we only need a standard through which we can compare the data, the sample data as well as the standard data, and if the peaks are matching, we can easily identify that this peak belongs to that particular compound. But for quantitative or quantification or quantitative analysis, we need to prepare a calibration curve. Now, since in the discussion so far on atomic emission spectroscopy, we realize that since no light source is used in atomic emission spectroscopy, which means that the excitation will not occur by absorption of light. Then what are the other modes of excitation? The other mode of excitation left is the heat or the thermal energy. So since we are not using light radiations, we are using thermal energy or heat to excite the samples. Now, as we are already using heat for atomization of the sample in atomic absorption spectroscopy, and then that atomized sample is excited with the help of light radiation, but here the whole job of atomization as well as excitation is being done by the thermal energy which is provided by the atomizer, and therefore the atomizers that are used in atomic emission spectroscopy, they are of very high effectivity, they are of very high power, so that they can provide, so that they can achieve very high temperatures that are not required in atomic absorption spectroscopy. And there are three types of atomizers or excitation sources that are being used here. Excitation means to, first of all, they atomize the sample, converting the sample in the solvent to, they first of all remove the solvent, desolvation, followed by vaporization, followed by vaporization, then dissociation of these molecules into individual atoms, and finally one more process called as excitation, in which the same excitation source provides extra energy, causing the electrons to be promoted to the higher energy state, and therefore these excitation sources have excessive energy. There are three types of excitation sources here. The flame excitation source, of course, the energy of flame in this case a little bit higher, but still we cannot analyze all the metals, especially those metals which require high temperature, by this technique. So for those metals we either go for furnace excitation, or the best way, because plasma excitation achieves very high temperature and the thermal energy that it provides is very high, that can immediately perform atomization as well as excitation of almost all the metals, and therefore it increases the scope of this atomic emission spectroscopic technique as well as makes it versatile. The instrumentation of AES is almost similar to the AAS, except the very known fact that we do not need a light source here. So in case of atomic absorption, we have nebulizer, we have first of all we have a nebulizer, then we have atomizers, then in atomic absorption spectroscopy we have a nebulizer, we also have atomizers, then we have a light source, followed by a monochromator for selecting specific wavelengths, detector, and amplifier. But in this case we do not need a light source, so I strike out this light source. We only have a nebulizer over here, we have an atomizer, or it is also called as excitation source because it is also exciting this sample by promoting electrons. We have monochromator, followed by detector and amplifier. So in terms of components, it has no light source, so one component is lesser as compared to atomic absorption spectroscopy. This is the flow diagram of atomic emission spectroscopy, which is quite similar to atomic absorption spectroscopy, with the fact that it does not have a light source. Again, as you can recall the slide where I have explained you the instrumentation of atomic absorption spectroscopy. We have a sample holder in the form of a standard flask or a conical flask where we put the inlet pipe of the nebulizer. This nebulizer has pump which sucks in the sample and mix this sample with fuel and oxidant. The common fuel for flame atomizers are either hydrogen gas or acetylene gas, CH triple bond CH, while the common oxidants are oxygen or maybe air or nitrous oxide. They are used. This nebulizer this nebulizer sucks in the sample at a controlled flow rate and then mix it with fuel as well as oxidant. The excessive sample is drained out from this pipe. From this pipe, it can be drained out while the sample is uniformly mixed with fuel and oxidant to convert it into an aerosol. So the sample is here, it is in the form of solution, but before injecting into the flame or into the excitation source or atomizer, it is converted into an aerosol just like we did in atomic absorption spectroscopy. And once this aerosol is formed, it is in the form of a spray in which liquid droplets from this solution are dispersed in water. As you all know that aerosol is a colloidal system. Aerosol is a colloidal system where liquid is dispersed in gas. So the liquid from this solution containing our target analyte molecules is mixed with gas, is dispersed in gas, and then at a controlled flow rate it enters into the atomizer or the excitation source, where excitation is provided either by flame, which is called as direct excitation, or by some electric discharge. And the third and best way is to use a plasma. These three, either of these sources are used as excitation source, and when the high temperature, high thermal energy is provided by this excitation source, it immediately converts the liquid, the aerosol containing liquid droplets in which the sample is present in the solvent and the whole system is dispersed in a gas. This high temperature provided by the excitation source immediately causes drying up of the sample by evaporation of the solvent, and then it dissociates the molecule or the compound into individual atoms, followed by their vaporization. Finally, the extra amount of energy that is being provided by the uh, excitation source is utilized for excitation of the sample atoms. And when these sample atoms are excited, their electrons are promoted, as you all know, to the higher level. And when these electrons return back from the higher level back to the ground state, they emit photons. Then these photons enters into the monochromator by an entrance slit. Now you are aware of all these technical words. What is a monochromator? I have already explained you in the previous lecture of atomic absorption spectroscopy. So you all are aware about the monochromator and how a monochromator is formed by using an entrance slit and an exit slit, along with few mirror like a collimating mirror and a focusing mirror. And the most important thing is the prism or a grating, which is used to disperse light into individual regions. So this light that is being emitted by the relaxation or the deactivation process enters through the entrance slit, and they falls on the grating to be dispersed into individual radiations and falls on the focusing mirror, which reflects it towards the photosensitive detector. And again, as you all know, that since in this technique also we are measuring the light photons, so we again use the same detector, the photomultiplier tube, which consists of a photosensitive anode which creates electron when it receives photons, and these electrons are called as primary electrons. These electrons then falls on these dinodes to create more secondary electrons, which ultimately reaches to the anodic side, and an amplified current signal is obtained, which is displayed in the readout device or the computer. So this is a flow sheet or a working diagram of an atomic emission spectroscopy, and in this way we can perform the analysis of elements of interest present in various metrics like water. It may be tap water, it may be wastewater, or the water from a river, of course after filtering the river water, because it must not contain any suspended impurities, as it will block these pumps or the pipes which are connecting these nebulizer with the atomizer. So we avoid such suspended material, and in addition to water sample, the same technique can be used for analysis of blood, urine, serum, or any other sample like juice sample in industries. With this, I hope that you have got a brief idea about the working of atomic emission spectrophotometer. In the next few lectures, we will discuss about its components and how plasma is being generated, which is very important for you to learn for competitive for competition purposes as well as for job interviews. Till then, thank you very much.